Um, so exam 3, I believe, is next Monday. That's how I interpreted my calendar. Um, and the topics for exam 3 are, remember, it's cumulative, so everything starting at the beginning, but up through linkages. And one thing, I think sometimes I don't say this as much as I used to, but really, so I think there's kind of a tendency. I mean, I remember feeling this way when I was in college, that you study until you understand the concepts or whatever. But what I'm really trying to do is put sort of tools in your tool belt for calculations. And what you really need to do to get ready for my tests is, first, you got to understand the thing. But after you understand it, that's when you have to do the repetitions. Okay, so you should be just trying to go through these problems just one after another. Like, that's the way to solidify this stuff. The problems that I'm going to put on the exam are not fundamentally different than the problems you see in homework. It's just about building that kind of muscle memory, like, of how to go through problems like this. And so, since it's cumulative, remember, there could be questions on vectors and differential equations, all the old stuff, particle kinematics, all that stuff. So glance back at the old problems too. And then one thing, kind of a practical issue with linkages problems on exams. Linkages problems obviously take a long time, Well, we do have 80 minutes in this class, so I have a little more room than in 50-minute classes to do linkage problems. But the way I get around that is, I'll often break up linkage problems into sort of different steps. I'll do things where I'll give you a linkage and I'll say, draw the free body diagrams for each one of the bodies. Or I'll say, come up with the equations for each one of the bodies. Okay, like the Newton's laws equations. Or I'll say, come up with the constraint equations that you need for this linkage. Okay, it's pretty rare that I'll have you go through a whole calculation and come up with numerical values, but I'll kind of ask you to do those steps. Okay. Any questions about the test? Yeah.
I know we kind of talked about rolling without slipping, but it never really came up in a test. Would that still be considered to be possible?
Yeah, that could be on tests. I guess anything that you've had homework problems assigned on, you should think of that as fair game for exams. Okay, so number 8, I think I only assigned 2 problems last time. So I'm going to call this body 1 and this body 2, and I'm going to call the joints A, B, and C. And it gives you the angles. They're connected at the midpoints. So let's just go through the steps. Well, actually, let's, how many people have finished this problem already? Okay, not too many. So let's do this. Sorry if this is redundant, James, but so we're going to start by coming up with the equations for body one. So everybody, get with the people next to you. You can do it by yourself if you want, but at least sort of compare answers as you go and come up with the Newton's laws equation for body one. And then I'll go through it. We'll go to the next one and just make sure everybody's rolling with this stuff. Same page. So we're on member one. Is there a fixed point on member one?
Point A.
Yep. So point A is the about point. So the mass moment of inertia is 1/12. How long are these things? Yep. 20 kilograms each, yeah. So 20 times 1.5 squared. And then the parallel axis theorem part is 20 times 0.75 squared. And what do you get for that? 15? Ooh. So nice and clean. And then the free body diagram. We have a reaction force, I'll call it RA at the pin. At the midpoint of the beam, we have a weight of 20 times 9.81. Then we have the force vector on 1 by 2. And then on one of the two members, we have to apply this 500 Newton force, not on both of them. The people who took statics with me, maybe you remember, I always put it on the lower number of the two members that are connected. And so...
Wouldn't that just build off the gravitational force, making it...
So, yep. And so we have a 500 Newton force there. If you put it on the other member instead, there's no problem with that. In the end, you'll get the same stuff. Yes?
It wouldn't work if you put that 500 Newton force on both.
Correct. It would not work. It would be like applying 1,000 Newton force on the system. And actually, it makes sense if you think about it this way. Imagine that I didn't draw that 500 Newton force right at that pin. Imagine I drew it 1/10 of a millimeter to the left. Okay. So then it's definitely acting on member 2. Okay. Like intuitively, does that seem like that would change the behavior of the problem? Not really, And so you could think of, and so now think of a 500 Newton force applied just to the left of the member and a separate of the pin, and a separate one, 500 Newtons, just to the right of the pin. That what you're really doing is just basically drawing a system where you have a 1,000 Newton force. And that's what you would get if you applied that 500 to both of those two members.
Whenever we have the all the joints numbered, we just assign it to the lowest one, right?
That's right. That's how I always do it in statics. There's no rule that you have to do it. It's just a way to make sure that you're not double counting forces. You also can just, when you look at it, just always make a choice, like where does it look like it's acting, Maybe it, if you think it looks like it's acting on member 1, put it there, Okay, so I'll give you a little more time. Anybody, I assume some people need more time to get to the equations. Is that right? Who's done with the equations?
Or just member 1?
Yeah, just for member 1. Okay, let's do 3 more minutes. So now I'm going to go do the table. We have rho, force. I should mention that in the solutions, a bunch of the solutions have a table with more columns in it. If you notice that, there's a P and then an A. And the way that works, so that's the way that I used to do it. I don't do it anymore because it's just cluttered. It's more stuff to remember. So when you see these solutions, to make it match the way I do it now, you can just cross out those first two columns. But the way this works is if you have the coordinates of P and you have the coordinates of A, you can just take P minus A to get that row vector. So that's why I used to do it like that. But I've come to just prefer remembering the definition of the row vector and just calculate the row vector however you want to calculate it. All right, so our about point is down here. So I'll start with RA. The row vector is 0. The force vector is RAX, RAY. Cross product is 0. Then I'll go to the weight. The row vector is 0.575, 0.482. Force vector is 0, negative 196.2. So that's negative 112.82. Then the force vector F12, it's at the same point as that weight force, so the row vector is the same. The force is F12x, F12y. The cross product is 0.575 F12y minus 0.482 F12x. And then the 500 Newton force, that's at the same point also. So the row vector is 0.575, 0.482. The force is 0, negative 500. Cross product is negative 287.5. This has a fixed point, so we don't need Newton's second law. And so we go straight to rotational Newton's second law. And that says negative 112.82 plus 0.575 F12y minus 0.482 F12x minus 287.5 is equal to the mass moment of inertia, 15, times the angular acceleration of body 1. And now I'll just rearrange this. This is our first equation from our big final system. So I'll write it as negative 0.482 F12x plus 0.575 F12y minus 15 alpha 1 is equal to 400.32. Okay, so where are we now? Can we solve anything? No, we have one equation, 3 variables. So there's nothing we can do yet. These are F1, 2, X and Y components, and alpha 1. Okay, so now go on to member 2. And I guess I'll do the same thing. I'll give you a couple minutes, then I'll draw the free body diagram, and then I'll give you a couple more minutes to finish with the equations. Okay, let me draw the free body diagram for member 2. Well, let me go through the steps. So step 1, is there a fixed point on member 2? Okay, so the about point is the center of mass. And so the moment of inertia is 1/12 times the mass of 20 times 1.5 squared. And what do you get for that? 3.75 kilogram meters squared. Notice how big the contribution of the parallel axis theorem was from the first one. You know, you can definitely have cases where that parallel axis theorem part is much, much bigger than the sort of than the moment of inertia about the center of mass. And then the free body diagram. We have the weight at the center, 196.2. We have a pin and slot joint at C. It's not restricted left and right, so there's no force horizontally, but it is restricted from moving up or down, accelerating up or down. So there's going to be a force this way to keep it from sinking into the ground or jumping off the ground. So I'll call this RC. We know the direction of that. And then there is the force on body 1 by body 2 acting here. And since we already have the force on 1 by 2 as a variable, I'm going to use Newton's third law here and call this negative F12. We've already put in the 500 Newton force, so we don't put it in here. And so this is it. Any questions about the free body diagram? Okay, so keep going. And so for the table, our about point is the center of mass this time because there's no fixed point. I'll start with this force negative F12. The row vector is 0. The force is negative F12x, negative F12y, 0. Then I'll do the weight. Row vector is also 0. Force is 0, negative 196.2. Cross product is 0. And then the last force is RC. The row vector is positive 0.575, negative 0.482. That force vector, you could have done it downwards too, and then that force would have been 0, negative RC. Everything will work out in the end. I did it upwards, so this is 0, positive RC. And so the cross product is 0.575 RC. Do we need Newton's second law for this one? Yep. And so we'll add up all of these. So negative f12x, negative f12y, plus 0, negative 196.2, plus 0 RC is equal to the mass, 20, times the acceleration of the center of mass. And whenever we have these accelerations of the center of mass, those become variables. So I'm going to call this A2x and A2y. And I'll rewrite these as equations for the big system in a second. Now we'll go to step 6, which is rotational Newton's second law. So here we're going to add these up and set them equal to I alpha. So we have 0.575 RC is equal to 3.75 alpha 2. And so our equation 2 star for our big system says negative f12x minus 20a2x is equal to 0. Our equation 3 star says negative f12y plus rc minus 20a2y is equal to 196.2. And then our equation 4 star says 0.575 RC minus 3.75 alpha 2 is equal to 0. Any questions about that? Okay, so now we have 4 equations. How many variables do we have? We have, it should be 7, hopefully. So F12 and alpha 1. And now we also have A2. That's 2 more. So now we're at 5. RC is 6. And alpha 2 is 7. And it's always good to make sure as you go along that things are working out the way they are supposed to. But when I said we should have 7 variables, I wasn't saying that based on counting the variables, which we just did and saw that it matched. I was saying that by thinking about the number of constraint equations that we were going to need to have. So what are the constraint equations that we're going to need? We're going to need to say, so we don't have to worry about this point A. That we're assuming that that's a fixed point. That's sort of baked into our whole calculation. So we don't need one there. But we do need to say that members 1 and members 2 don't fly apart at that point where they're connected, that middle point. So that's setting 2 accelerations equal to each other. That's 2 equations, or 2 acceleration components equal to each other. And then down here at C, it's fine if it accelerates left and right. We expect it to. But we are going to specify that it can't accelerate up or down. Okay? And so that's only 1 more equation. And so we have a total of 3 constraint equations. So based on that, I knew that if things are working the way they should, we should have 3 more variables than we have equations. Okay, so now take a few minutes and do the constraint at B. Okay, so this is going to say This constraint is going to say we're going to calculate the acceleration of the point B on body 1. We're going to calculate the acceleration of the point B on body 2, and then we're going to set them equal to each other. So let's start out with member 1. I'll give you a couple minutes.
There is no angular acceleration, right?
There's no angular velocity. That's right. The angular accelerations, though, are alpha 1 and alpha 2. Okay, so start by calculating the acceleration of B on member 1. Okay, so this one has a fixed point. Body 1 has a fixed point. And so this is just a circular motion around a fixed center, that fixed center being the point A. And so we don't need relative motion here. We just need the watermelon equation. So the acceleration at B is equal to all right watermelons will rot. And our alpha vector is 0, 0, alpha 1 because we're doing body 1. Our omega is 0, even though it didn't say that. It should have. And our r vector, what's the definition of the r vector?
The vector from the center of to the point of
Center of circular motion to point of interest. Perfect. Yep. So this is 0.575, 0.482, 0. And so the acceleration of B is equal to 0, 0, alpha 1 crossed with 0.575, 0.482, 0 plus this thing that's 0. And you get negative 0.482 alpha 1, positive 0.575 alpha 1, and 0. Any questions about that? Okay, so now do member 2, and then come up with the 2 equations, constraint equations. So now we're going to calculate the acceleration of B according to member 2. This one doesn't have a fixed point, so we have to use relative motion equations. So the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of body 2 plus the acceleration of the center of mass of body 2 relative to the ground. And this one has an alias. It's known on the streets as A2. And then this guy is the watermelon equation.
Isn't the center of mass at B?
The center of mass is at B, yes. And what's the definition of the r vector? Yeah.
From the center of circular motion to our point of interest, and in this case,
Yes.
it's 0.
Perfect, exactly. So the r vector is going to be 0 here, and so this green circled part is going to go away. But we don't know that yet because we're stupid.
Okay.
Okay, so we're gonna just write it all out and see. So the acceleration of B relative to the center of mass is alpha cross r plus omega cross quantity omega cross r. Alpha is 0, 0, alpha 2. Omega is 0, 0, 0. But the thing that really changes the game here is that r is 0, 0, 0. And so So the acceleration of B relative to the center of mass of 2 is equal to 0. And so, therefore, the acceleration of B relative to the ground is 0, 0, 0 plus A2. Okay? And now we can put these two things together. Finally, the constraint equation says negative 0.482 alpha 1, 0.575 alpha 1, and I guess since I've been carrying it through until now, I'll keep the 0 at the bottom, but you can drop that whenever you want. This is equal to A2x, A2y, 0. And so our equation 5 star says negative 0.482 alpha 1 minus A2x is equal to 0. Yes?
The angular acceleration, should that be of 2?
I think that was 1 because we got that equation from, we were calculating the acceleration of B on body 1.
So the two accelerations equal to each other.
Yeah. And then 6 star. The reason we don't have usually we have an alpha 2 also, but we don't here because the watermelon equation went to 0. And so the second one says 0.575 alpha 1 minus A2y is equal to 0. Okay, so there's our equations 5 and 6. We need one more constraint equation, and that is the constraint at C. So now take a couple minutes and calculate the 7th equation. Okay, so the constraint at C. So we're going to use body 2. Does body 2 have a fixed point?
It doesn't.
Does not, and so we're going to have to use relative motion. So the acceleration of C relative to the ground is equal to the acceleration of C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. And this is A2. And this is the watermelon equation. So the acceleration of C relative to the center of mass of 2 is alpha cross R plus omega cross quantity omega cross R. Alpha is 0, 0, alpha 2. Omega is 0. R is 0.575, negative 0.482, 0. And so the acceleration of C relative to the center of mass is equal to 0, 0, alpha 2 cross 0.575, negative 0.482, 0, plus this stuff that goes away. And we get positive 0.482 alpha 2, positive 0.575 alpha 2, But that's not a constraint equation. That's just an expression for the acceleration. Wait, that's not even an expression for the acceleration yet. We have to put it together. So the acceleration of c relative to the ground is this plus a2. So 0.482 alpha 2 plus a2x. 0.575 alpha 2 plus a2y. And then the constraint comes from saying this expression tells us what the acceleration of that point C is. The y component needs to be 0 because of the nature of that joint. And so the constraint equation, this is 7 star, says 0.575 alpha 2 plus a2y is equal to 0. And then you have your system of 7 equations for 7 variables. Anybody have any questions about that? Okay.